mappings phi from V to W change if we change the basis in V and W. So we already know that if V is a vector space with basis vectors V1 through Vn, then every vector V in the vector space can be uniquely written as a linear combination of those basis vectors. The natural question to ask, however, is how do we quickly change from one basis to another? To do this, we simply write the old basis vectors in terms of the new basis vectors and create a matrix with these new vectors as columns. We saw that in the preceding video. To change basis from B to C, we write the basis vectors B in terms of the basis for C. Those vectors are the columns of the change of basis matrix from B to C. So if we take a vector V, 1, 0, as a standard in our standard basis, and we take bases B, 1, 2, 3, 4, and C, 7, 3, 4, 2, we can find that vector V in terms of basis B and basis C. We've already seen how to do this. We want to put it in terms of B. We take V, 1, 0, and we create a linear combination A1 times the first basis vector in B plus A2 times the second basis vector in B. Solving this, we get A1 equals -2 and A2 equals 1. So the vector 1, 0 from our standard basis is now -2, 1 in basis B. Now, if we want to convert the basis vectors of C to be in terms of B, we can do it exactly the same way. Alternatively, we can convert the basis vectors of B to be in terms of C, and then multiply by our change of basis matrix. So if we're to put basis vector 1, 2 in terms of C, we get -3 and 5.5. If we're to put 3, 4 in terms of C, we get -5 and 9.5. So those vectors, as taken as columns of the change of basis matrix, give us the matrix -3, -5, 5.5, 9.5, which we can multiply by the vector 2, 1 from basis B to get the vector 1 and -1.5, and that's vector V in terms of basis C. If V is a vector space, and A, B, and C are all bases of V, and if we can create a matrix P that takes basis A to basis C, then we can represent matrix C that takes basis A to basis C as the product of a matrix P that takes basis B to basis C times another transformation matrix P that takes basis A to basis B. So thinking about change of basis this way, we can fairly easily move from one basis to another as long as we have the change of basis matrix at our disposal. The image and kernel of a linear mapping are vector subspaces with certain important properties. Let phi take V and map it to W, and let it be a linear mapping. We'll define the kernel as kernel of phi equals the set of all V from our vector space V, such that phi of V is equal to 0. The image of phi, which we'll call IM of phi, is the set of W in the codomain such that there exists a value v in v such that phi of v is equal to w. We typically refer to v and w as the domain and codomain. Intuitively, the kernel is a set of vectors in v that maps phi into the neutral element in w. The image is a set of vectors w that can be reached by mapping something from v using phi. And you can see that in the diagram on the slide. Here's an example. We'll let phi be the transformation that maps vectors x, y, z to the product of the matrix 1, 0, negative 1, 1, 2, negative 1, 1, 0, 1 times x, y, z. What's the kernel? Well, the kernel is a set of things that map to 0. So what we're looking to do essentially is solve the system of equations given by 1, 0, negative 1, 1, 2, negative 1, 1, 0, 1, all times x, y, z equals 0, 0, 0. If you use Gaussian elimination, you'll find that that's actually the 0. The x, y, and z all have to be 0. On the other hand, we modify the example slightly and make our matrix 1, 0, negative 1, 1, 2, negative 1, 1, 0, negative 1, and we look at the kernel of phi. When we apply Gaussian elimination to the system of equations, we end up with 1, 0, negative 1, 0, 1, 0, and then a row of zeros, which means we have a free variable. So from here, we know that x minus z has to equal 0, and y has to equal 0. So as long as x and z are exactly the same, then we're going to end up with a 0 vector. So the kernel of phi is the span of the vector 1, 0, 1 transpose. Consider a linear mapping phi from v to w where v and w are vector spaces. It's always true that phi of the 0 vector in v is equal to the 0 vector in w, and therefore 0 is always going to be in the kernel of phi, which means the kernel, the null space, is never empty. The image of phi is a subset of w, and the kernel of phi is a subset of v. Phi is injective if and only if the kernel of phi is the 0 vector. Now, if we consider a matrix A, n by n, and a linear mapping phi from Rn to Rm, we'll let phi of x be Ax. Then for A, the matrix A1 through An, where the AIs are the columns of A, we have the image of phi is equal to the set of Ax, which is equal to the sum of xi times ai for all xi in R, which is the span of our column vectors a1 through an, which is a subset of Rm. That is, the image is the span of the columns of A, also called the column space. Therefore, the column space, the image, is a subspace of Rm, where M is the height of the matrix. We'll let phi be a transformation from R4 to R2, given by phi of a vector equals the matrix 1, 2, negative 1, 0, 1, 0, 0, 1 times the vector. When we multiply this out, we get x1 times the vector 1, 1, x2 times the vector 2, 0, x3 times the vector negative 1, 0, and x4 times the vector 0, 1. The image of phi, by what we just saw on our previous slide, is equal to the span of the vectors 1, 1, 2, 0, negative 1, 0, and 0, 1. The kernel has to be computed by solving ax equals 0. And to solve that homogeneous equation, we use Gaussian elimination. If we use Gaussian elimination and transform our matrix into reduced row echelon form, we can use the -1 trick to compute the basis of the kernel. And so the kernel is going to be the span of 0, 1/2, 1, 0, and negative 1, 1/2, 0, and 1. This concludes our brief treatment of linear algebra. Obviously, linear algebra is a much larger topic than what we discussed in these short videos, but this will give us enough to move on to analytic geometry, where we're going to discuss more the physical properties of matrices and vectors.